Deep space doesn't test you, it erases you. And that's what this video is about. Not space is hard, but why right now the universe makes long-term human survival out there basically impossible. If you think we can just engineer our way through it, stay tuned, because the void has a very different answer. There is one basic problem with your body in space. You're mostly water, and space is a hard vacuum. How does that mismatch actually kill you step by step without any movie exaggeration? Right now at sea level, the air around you pushes with a pressure of about 101 kilopascals, roughly 1 bar, the same as about 14.7 pounds per square inch. Deep space is essentially zero. When you go from inside a spacecraft at normal pressure to the vacuum outside, that's a drop of about 101,000 newtons per square meter in one jump. You don't explode, but every system in your body was built assuming that to background air pushing on you. Take that away, and the weak points show up in seconds. The first system that fails is your lungs, and they fail fast. Why your lungs first? Inside your chest, air is still at roughly 1 atmosphere, while outside the pressure has crashed to almost nothing. That trapped gas wants to expand. If you panic and hold your breath, your chest stays tight, so the expanding gas pushes out on the thin walls of the tiny air sacs, the alveoli. Those sacs are only a fraction of a millimeter thick. Enough pressure difference and some of them tear. That tearing can push air into places it should never go, into the space around your lungs, into your chest cavity, even into your bloodstream. Air bubbles in blood vessels can block flow to vital organs. So holding your breath, the thing that feels safe, is actually the most dangerous move in a sudden decompression. If instead you force yourself to exhale as pressure drops, you let that gas escape. That reduces damage, but it doesn't solve the core problem. You've just emptied your lungs into a vacuum. With no air left to breathe, your blood oxygen level starts to fall. Your brain uses a lot of oxygen, so it is the first to notice. After about 10 to 15 seconds, your vision narrows, you lose fine control, and you black out. You don't freeze, you don't explode, you simply run out of usable oxygen. Your heart might still beat for a short time, but from your point of view the lights are off. So your lungs are either damaged or empty, your brain is losing consciousness, but you're still warm. Where does the boiling body idea come from then, if you're not actually on fire or in some kind of oven? Here's the twist. How can water boil at body temperature without adding any heat? Boiling is not just about temperature, it's about pressure. At 37 degrees Celsius, normal body temperature, liquid water needs roughly half an atmosphere, around 47 kilopascals to stay liquid. Drop below that pressure and it can start to boil at the temperature it already has. In deep space, the pressure at your exposed surfaces is far below that. So the thin films of liquid on your body, your saliva, your tears, moisture on your tongue, the wet surfaces of your eyes, are suddenly in an environment where they can't stay liquid. They start to flash into vapor. It isn't a big dramatic geyser, but it is real boiling. Little bubbles form, gases come out, those surfaces start to dry and swell. Your skin actually holds most of your body together like a natural pressure suit, so you don't inflate like a balloon. But wherever tissue is directly exposed, conditions are brutal. Your tongue can puff and crack, your eyes can lose moisture very quickly, the inside of your mouth can feel like it's being stripped. This is your own body water crossing the line where its solid liquid-gas balance changes right in front of you, simply because the air outside has disappeared. If that's happening to your saliva and tears, what about the blood and fluids deeper inside you? Do they also start boiling away? This is where the details matter. Your blood is inside vessels, under some pressure, and your circulatory system has structural strength. That means your blood does not instantly boil when you hit vacuum. It stays liquid for a while. But stays liquid does not mean stays safe. Gases like nitrogen and oxygen are dissolved in your blood and tissues. When the external pressure drops suddenly, those gases start to come out of solution, forming bubbles. This is the same basic effect divers fear when they ascend too quickly. Decompression, sickness, the bends. The difference is scale. A diver might go from 3 or 4 atmospheres back to 1, You've gone from 1 to almost 0 in one shot. Bubbles can form in joints, causing pain, but also in muscles, in the spinal cord, in the brain, and in the tiny vessels that feed your tissues. They can block blood flow and damage cells. Your body has no time to adapt, no time to slowly off-gas. You've taken the maximum decompression hit possible in seconds, so you have lungs that can rupture, surface fluids that can boil, and internal fluids that can fill with gas bubbles. The obvious answer is, don't expose the body at all. Wrap it in gear that provides pressure. Use technology to replace the missing atmosphere. That's what a spacesuit does. But how close to perfect does that technology have to be for you to survive even a few hours? A modern spacewalk suit is basically a small spacecraft around your body. Instead of giving you full Earth pressure, about 101 kilopascals, it runs at roughly 30 to 40 kilopascals inside, around 1/3 of an atmosphere. To make that breathable, it switches to almost pure oxygen instead of the 21% oxygen mix you get on Earth. That way, even at lower pressure, the actual amount of oxygen hitting your lungs every breath is enough. That pressure is just high enough to keep your blood liquid, keep your lungs from collapsing, and stop your body fluids from boiling. The suit also regulates temperature, scrubs carbon dioxide, and gives you communications and power. From your point of view, it just works. You can move, talk, and do your job, but keeping that bubble stable is a constant fight. Every seam, every joint, every connector is holding back that tens of thousands of newtons per square meter pressure difference. The fabric and metal experience stress every time you bend an arm or flex a glove. The suit material slowly ages, tiny cracks and wear points build up. On top of that, space is full of micrometeoroids, small pieces of rock or metal flying at tens of kilometers per second. A grain only a few millimeters across can carry as much energy as a bullet. If it hits just right, it can punch a pinhole through your suit. Your life depends on several systems working at the same time without serious failure for the entire duration of the spacewalk. Lose pressure, lose cooling, or lose oxygen flow, and the clock drops from hours to seconds or minutes. There is no backup environment around you, only hard vacuum. On Earth, a small pressure change is just a storm, something you can mostly ignore. How different is deep space, where the background is not a soft cushion of air, but nothing at all? Here is the key point. On Earth, the atmosphere is thick and heavy. If pressure in one place drops a little, air flows, weather happens, things smooth out. You're always surrounded by this huge mass of air that can buffer changes. Even inside buildings or vehicles, the outside air is a safety net. In deep space, there is no safety net. Your ship or station is a bubble of gas at maybe around 101 kilopascals inside, 0 outside. A single leak is not a minor issue. It is the only air you have trying to escape into an infinite vacuum. There is no outside pressure to slow the leak. There is no wind to push air back in. Every gram of air you lose is gone unless you have tanks and systems to replace it. That means survival is not about being tough, it is about being perfect. Every weld, every valve, every panel, every hatch must hold. Every sensor that watches pressure must work. Every emergency drill must be right the first time. There is almost no margin. You're keeping a small pocket of Earth-like conditions alive in a universe that defaults to 0 pressure, 0 air, and no second chances. And this is only one layer of the problem, the pressure layer. Even if you manage that perfectly, there is another hostile fact waiting outside your hull, just as unforgiving. How do you stay alive in a place that is almost at absolute 0, but can also heat you like a powerful oven, sometimes at the same time? Space is only a few degrees above absolute 0, so why don't you just freeze solid the moment you're exposed to it, and how can that same environment also cook you from one side like an oven? Both things are true at the same time, and if you don't understand that, you cannot understand why deep space is so deadly for humans and for the machines keeping you alive. First, the cold. Deep space sits at about 3 Kelvin, roughly minus 270 degrees Celsius, around minus 454 degrees Fahrenheit. That number sounds like instant death, but that's not how your body loses heat. On Earth, you get cold because air or water is carrying heat away from you by conduction and convection, molecules hitting your skin and stealing energy. In deep space, there is basically nothing there. No air, no water, almost no particles at all. So the usual ways you cool off just stop working. You're left with one channel: radiation. Your body, at around 37 degrees Celsius, constantly emits infrared light, like a weak heater. A typical adult radiates on the order of 100 watts just by existing, roughly the power draw of a small light bulb. That is energy leaving you, photon by photon, into the black background of the universe. Because radiation is relatively slow, you don't instantly freeze. Even naked in vacuum, if pressure and oxygen weren't a problem, you would cool over minutes, not milliseconds. Your skin would start to chill, your core temperature would drop gradually, and hypothermia would build up. But in reality, you're unconscious from lack of oxygen in seconds, and dead from that long before the cold finishes the job. Now put a spacesuit around you, and this gets even more complicated. The suit insulates you, so your own radiation can't easily escape directly, and you also generate more heat when you work. The cold of deep space is not a giant freezer that automatically keeps you safe. It's just a sink, a place you can dump heat into, if and only if your systems are designed to do it. That brings up the opposite side of the problem. If the background is so close to absolute zero, how can you overheat in space, sometimes in seconds? At Earth's distance from the Sun, the energy streaming in on a flat surface facing the Sun is about 1,361 watts per square meter. Call it roughly 1,360 watts per square meter. In more familiar terms, that's more than a kilowatt of power per square meter, similar to having a strong electric space heater pressed against each square meter of your suit or your spacecraft hull. With no atmosphere to scatter or soften that beam, your body presents maybe 1 to 2 square meters of area, depending on orientation. That means if you're in direct sunlight with no protection, the sun is trying to dump well over a kilowatt of power into you. Combine that with the heat you're already generating inside the suit, and you have a serious thermal problem. Surfaces facing the sun can climb well above the boiling point of water, easily over 100 degrees Celsius, if they are dark and uncooled. This is why space hardware looks shiny and white. The outer layers reflect as much sunlight as possible, and internal systems carefully control how much heat is absorbed and how much is rejected. For a spacesuit, the design has to keep the outer layer from overheating in sunlight, shield you from the direct beam, and still let enough heat escape that you don't cook inside your own life support system. So now you're trapped between two extremes: almost zero background temperature and intense solar radiation. On Earth, you just rely on air to smooth that out. You step into shade, feel a breeze, and your body adjusts. But in deep space, what happens when there is no breeze at all ever? On Earth, if you stand in 25 degrees Celsius air, about 77 degrees Fahrenheit, and you're too warm, the air moves around you, strips heat from your skin, and your sweat evaporates. That moving fluid is your main heat control partner. In space, there's no air, no water, no fluid outside your hull. The only heat transfer with the environment is radiation. That means if something is hotter than its surroundings, it must lose heat by glowing in infrared. And if something is colder, it can only warm up by absorbing light or contact with warmer objects. That's why spacecraft use large radiators, flat panels sticking out into the dark. Hot coolant flows through them, they emit infrared, and that radiation carries energy away. There is no open a window and let the hot air out option, because there is no air. Engineers have to calculate very precisely how much heat all the equipment will generate, how much sunlight will hit the vehicle from all angles, and how much radiator area is needed to keep everything in a safe temperature range. If they miscalculate even by a small margin, lines can freeze or electronics can overheat. Coolant pipes can drop below freezing, crack, and leak. Hardware in sunlight can creep toward temperatures that destroy components. There's no quick fix, no weather to help smooth the error. The physics is simple but unforgiving. And all this isn't just about the outside shell, it's also about what's happening across a spacecraft in the different lighting conditions. How bad can those internal temperature differences really get when one side is lit and the other is in deep shadow? Parts of a spacecraft that sit in direct sunlight can easily reach around plus 120 degrees Celsius, roughly 250 degrees Fahrenheit or more, if they're dark and uncooled. Surfaces in deep shadow with a view only to cold space can plunge to about minus 150 degrees Celsius, around minus 240 degrees Fahrenheit. That's a swing of roughly 270 degrees Celsius across a span of just a few meters. Different materials expand and contract by different amounts when you change their temperature. Metals, composites, polymers, they all react differently. If you bolt two materials together, and one wants to grow more than the other, when it heats up, the joint takes the stress. As the vehicle orbits, rotates, or just moves through varying light conditions, everything heats and cools over and over again. That's called thermal cycling. Every cycle is like bending a paperclip a tiny bit, then straightening it and repeating. It doesn't break right away, but eventually it does. Over years, seals can crack, fasteners can loosen, thin structures can develop tiny fractures. Those tiny fractures can grow. The thing you are relying on to keep air in and vacuum out is being flexed by temperature alone, constantly, whether you notice it or not. So the hardware is being pushed back and forth by temperature. But what about you? Your body is a heat engine, running at about 37 degrees Celsius, generating hundreds of watts when you work. How does that system behave in a world where only radiation can move heat out? Your metabolism burns chemical energy in food and oxygen and turns a lot of it into heat. At rest, you might generate around 80 to 100 watts. When you work hard, especially in a stiff suit, that can easily climb into the 500 to 800 watt range, or even more. On Earth, your body deals with that by increasing blood flow to the skin and making you sweat. Evaporation carries heat away, and airflow boosts that process. Water and moving air are your main cooling tools. In a spacesuit, none of that can touch the outside environment. Your sweat gets collected, your skin is covered, and the heat has to travel from your body into cooling garments, then into circulating fluid, then into heat exchangers, and finally into radiators that dump it as infrared. That whole chain depends on pumps, valves, sensors, and power. If the cooling flow is too low, you overheat. Your core temperature rises, you get dizzy, your performance drops, and you're on the path to heat stroke. If it's too high, you chill, your hands and feet go numb, and your muscles stop working efficiently. The control system has to keep you in a narrow range, not too cold, not too hot, while the external environment swings between deep cold and intense sunlight. And while your own workload changes from minute to minute, there is almost no slack in that system. A blocked coolant line, a stuck valve, or a software glitch can turn a spacewalk into a medical emergency with nowhere to sit down and cool off and nowhere to warm up. So by the time you've solved pressure and you've tamed this brutal thermal environment, you've already built a complex, fragile bubble of technology around your body. But there's another threat that goes straight through walls, suits, and skin, without caring about temperature at all. High-energy radiation that treats both you and your electronics like targets. How do you stay alive in a place where the background environment is constantly firing high-energy particles straight through your body, your brain, and your ship? Not heat, not cold, but radiation, invisible and non-stop, that treats you like a target instead of a passenger. Once you leave Earth's magnetic field, you lose one of the biggest protections you have, and you start to meet galactic cosmic rays directly. These are mostly protons and some heavier atomic nuclei that have been accelerated to speeds close to the speed of light by things like supernovae and black hole environments. Their energies are measured in billions of electron volts in the giga electron volt range. That's enough that a single heavy ion hitting a strand of your DNA is like a tiny projectile punching straight through the molecule. On the International Space Station, still partly inside Earth's magnetic shield, astronauts take in around 0.3 to 1 millisievert of radiation per day. That's already several times higher than what you get on the surface. Deep space, fully outside the shield, pushes that higher again. Over a long mission, those daily doses add up. This is not like an X-ray at the dentist that you do once and forget about. This is a constant background, day after day, year after year, slowly increasing your total lifetime dose, so you're being hit all the time, even on a quiet day. But what happens when the quiet ends and the sun itself becomes the weapon? The sun does more than just shine gently. Sometimes it releases bursts of particles, solar particle events, when magnetic fields snap and reconnect. In those events, huge numbers of protons are thrown out at energies in the tens to hundreds of mega electron volts. This is not a soft drizzle, it's a concentrated stream. If you are unlucky enough to be in the wrong place with poor shielding, a single large solar storm can deliver a dose of a few sieverts. To translate that into human terms, a dose of around 1 sievert increases your long-term cancer risk noticeably. Around 4 to 5 sieverts taken in a short time can be lethal for many people. That is acute radiation sickness territory, vomiting, organ damage, and potential death in days or weeks. On Earth, you let the storm pass, maybe reroute flights, and the atmosphere and magnetic fields soak up most of the damage. On Mars transit, or on a mission into deep space with no planetary shield, you're betting your life that the sun does not produce one of its bigger events while you are exposed. That's not a bet you want to take repeatedly. So you decide to add shielding, thicker walls, water tanks, maybe special plastics. Why not just add enough material until the problem goes away? Radiation shielding is simple in concept and brutal in cost. To cut certain kinds of radiation roughly in half, you need a specific amount of mass per unit area, often measured in grams per square centimetre. For particles like protons, materials rich in light atoms like hydrogen in water or in polyethylene work well. You might be talking about thicknesses of several centimetres, which translate into tens of grams of material per square centimetre of surface. Now scale that to a real habitat. Say your crew module has around 50 square metres of surface that you want to shield well, enough space for a small apartment. If you want to put tens of grams per square centimetre over that, you quickly get into tens of tons of material. In metric, that's tens of thousands of kilograms. In imperial terms, you're now pushing the equivalent weight of several fully loaded semi-trucks worth of water or plastic, just to reduce doses to something acceptable. Every kilogram you add has to be launched out of Earth's gravity well and then pushed around the solar system. The rocket equation makes that extremely expensive, so you compromise. You might create a smaller storm shelter area with heavy shielding and accept higher doses elsewhere. You might use fuel and water tanks as part of the shield, but you don't get perfect protection. You're always trading mass, cost and safety. Even with that shielding, you're still taking hits. What does that mean for your cells over months and years when every ion track is microscopic damage? Radiation at the doses we're talking about does not just kill cells outright, it also breaks DNA, both strands or changes bases, creating mutations. Your cells do have repair systems. They cut out damaged sections and rebuild them. Most of the time that works. Sometimes it doesn't. A misrepair slips through. A mutation becomes permanent. On a long mission in low Earth orbit, astronauts already show signs of increased chromosomal damage and a small but real increase in long-term cancer risk. Take that same human body and put it in deep space with higher daily doses and stronger events for years instead of months, and you're stacking up mutations faster than your repair mechanisms evolved to handle. You may come home looking fine on the outside, but your chances of developing cancers decades later in the lungs, in the blood, in the digestive system are now higher. In deep space settlement scenarios, where people might spend large chunks of their lives outside strong magnetic shields, you're essentially asking entire populations to carry around extra tickets in a cancer lottery they never agreed to. And that is just the biology. The same high-energy particles that hit your DNA also slam into the hardware that's supposed to protect you. What happens when your ship's brain starts taking the same fire your cells do? Cosmic rays don't care whether they're travelling through a chromosome or a microchip. In electronics, a single particle can pass through a memory cell and flip a bit from 0 to 1 or from 1 to 0. That is called a single event upset. Sometimes it just corrupts a pixel in an image. Sometimes it hits more important parts like control software, guidance code, or life support logic. Over time, cumulative radiation can also permanently damage semiconductor structures, making them slowly fail. That's why deep space probes use radiation-hardened electronics, special designs and materials that can take higher doses before failing, and why critical systems have redundancy. Multiple computers voting on outputs, extra boards ready to take over. But in a crewed ship, you're not just protecting a camera, you're protecting navigation, propulsion control, power management, air recycling, water systems, and temperature control. If your main life support computer glitches because of a particle hit, your survival time might shrink to however long your backup systems work, or however fast you can switch to manual control if that's even possible. So now the situation looks like this. Your body is fragile, your DNA is under constant attack, and your electronics, the only things between you and vacuum, are also vulnerable to the exact same environment. You're trying to keep a pocket of low radiation, Earth-like safety in a place that constantly tries to overwrite both your biology and your technology. And even if you somehow manage that, even if you wrap yourself in mass and hardened chips and ride out the storms, the universe has another slow weapon waiting. One that does not need particles or vacuum to hurt you. It uses something simpler, just the absence of gravity itself, slowly tearing your body down from the inside. How do you stay human in a place where your body slowly forgets what gravity feels like and starts rebuilding itself for a world you can't safely live in? The moment you go into microgravity, close to 0G, your body starts recalculating. Every system in you is tuned for 1G on Earth, for standing, walking, lifting your own weight. Take that constant downward pull away, and your biology reads it as a permanent new normal, not a temporary trip. The result is simple and brutal. Your body starts taking itself apart. The first thing that really pays the price is your bones. On Earth, your skeleton is under load all the time. Your legs and spine support your body step after step, day after day. In microgravity, that loading almost vanishes. Your body looks at that and says, "We don't need this much structure anymore," and it starts to downgrade. Astronauts in orbit lose bone mineral density in key load-bearing regions, like the hips and spine, at around 1 to 2% per month. That's not a typo, per month. On Earth, someone with osteoporosis might lose that much in a year. In space, your bones can age a decade in a few months. The calcium and other minerals come out of the bone into the bloodstream, and if your body doesn't manage it perfectly, that can also stress your kidneys. Now project that into the future. After many months or years in microgravity, you return to 1G, or you move into a rotating habitat that simulates gravity. Those weaker bones suddenly have to carry load again. A minor fall, a bad landing, even a quick twist can cause fractures. You need your body at its strongest for planetary landings and emergencies. But microgravity quietly makes you more fragile the longer you stay. So your skeleton is thinning month by month, but bones aren't the only thing your body decides to optimize away. What happens to the muscles that were built to fight gravity all day? Your body is efficient, sometimes in ways that work against you. It keeps what you use and cuts back what you don't. On Earth, your leg muscles, your back, your core, all work constantly just to keep you upright in 1G. In microgravity, that demand disappears. You float, you push gently off surfaces, you drift from module to module. Those big muscles just aren't needed in the same way. Even with intense exercise routines, more than 2 hours a day on treadmills, stationary bikes, and resistance machines, astronauts still lose muscle mass and strength over long missions. The body is always asking the same question: do we really need all this tissue? In space, for load-bearing muscles, the answer tends to be no. Then think about the moment you go back into a gravity field. 1G on Earth, or even partial G on the Moon or Mars, suddenly feels like wearing a full suit of heavy armor. Just standing up can feel like work. Walking is difficult. Running or lifting becomes a serious challenge. Your reaction time, your ability to move quickly in an emergency, All of that takes a hit, and all of this is happening while something else inside you is shifting in a very literal way. The fluids in your body are moving to places they don't normally stay. What does your circulation do when down disappears? On Earth, gravity pulls blood and other fluids toward your legs. Your body compensates by tightening blood vessels and using valves and muscles to push blood back up to your heart and brain. In microgravity, that pooling stops. There is no down, so fluids spread out more evenly, and a lot of that volume moves toward your torso and head. The effects are easy to see and not subtle. Faces puff up, neck veins stand out more. Some astronauts describe feeling stuffy all the time, but deeper inside, the pressure in and around the brain can increase. The pressure of cerebrospinal fluid can change. Over longer missions, we've seen something more serious. Vision changes. The back of the eyeball can flatten slightly. The optic nerve can show signs of swelling and visual acuity can drop. For a short mission, that's a problem you monitor. For a multi-year deep space mission, that is a huge red flag. Permanent vision damage is not just inconvenient when you're trying to read a screen. It is mission-threatening when you're trying to dock a spacecraft, repair a system, or land on another world. So your skeleton is thinning, your muscles are shrinking, your head is filling with extra fluid. At the same time, one of your most basic senses, your sense of balance, is being fed nonsense. What happens to your brain when your inner ear no longer has a clear down to work with? Inside your inner ear, tiny structures filled with fluid and tiny crystals normally tell you which way gravity is pulling and how you're moving. On Earth, those signals line up with what your eyes see and what your skin feels. In microgravity, the gravity part disappears. The inner ear is still sending signals, but they no longer match your visual input or your expectations. The result is motion sickness, nausea, disorientation. Some astronauts feel awful for the first days, some adapt more quickly, but almost everyone feels something. Your brain can eventually reweight the signals, trust your eyes more, and build a new map of what normal feels like. But it's not a one-time fix. Every time you change motion in a new way, a spin, a thruster, burn, docking, undocking, you can cause new mismatches. Your brain can get confused again, and that can bring back nausea or disorientation right when you need to be sharp. Try doing delicate repairs, or handling an emergency checklist, when your body is telling you that every direction is down and sideways at the same time. So you might think, fine, let's just bring gravity back, we'll spin the ship, use centrifugal force and get close to 1G at the rim. That sounds like a clean fix. Why isn't it? Artificial gravity through rotation is real physics, not science fiction. If you build a ring with a radius of about 100 meters, and you spin it at roughly 3 revolutions per minute, the apparent force at the rim can be close to 1G. Walk on the inside of that ring and your feet feel pressed against the floor, just like on Earth. But the experience is not identical. When you move your head, or you walk radially toward or away from the center, you introduce Coriolis forces. The air and the ring are rotating. Your body is trying to move in a straight line, and the combination makes you feel the forces in directions that don't match what you expect. Turn your head quickly, and you can feel the world tilt or slide. Some people will adapt, some will get dizzy and nauseous, and the limits aren't fully known. Then there's the engineering side. A 100-meter radius ring is huge, longer than a football field across. To make it safe and livable, you're talking about a structure with mass in the hundreds of tons, rotating in deep space with bearings, connections, docking ports, and all the systems for life support, power, and communication. You need to keep that spin stable, handle vibrations, and survive micrometeoroid hits and thermal stresses for years or decades. So microgravity either slowly tears your body down, or you fix it with massive, complex, rotating structures that come with their own set of risks. There is no easy, low-tech fix for the fact that your biology expects 1G and deep space offers almost 0. And remember, even if you somehow solve gravity, real or artificial, you still haven't solved the most basic daily problem of all: How do you keep a small group of humans breathing day after day inside a sealed metal can that can never be opened to get some fresh air? How do you stay alive in a place where every breath you take is eating the ship that brought you there, molecule by molecule? In deep space, air is not background, it's cargo, it's machinery, it's constant work. Start with oxygen, because without it you're done in minutes. A typical human at rest uses around 0.84 kilograms of oxygen per day. Call it just under 1 kilogram. Put 4 people in a ship, that's around 3 to 4 kilograms a day, and over a year you're at about 1,200 kilograms, roughly 1.2 metric tons. Stretch that to 5 years, and you're looking at around 6 metric tons of oxygen, over 13,000 pounds, just to keep 4 lungs going in and out. 6 tons doesn't sound huge on Earth, but in spaceflight every kilogram is paid for in rocket fuel, hardware, and money. You don't just drop a few more tanks into the corner like extra water bottles. Those tanks have to survive launch vibrations, temperature swings, and micrometeoroid hits. They take up volume you don't have, mass you can't easily push, and once you've breathed them they're gone, so you can't run a serious deep space mission on bring enough and hope. You're forced into a harder mode, you have to recycle, turn something else into oxygen over and over for years with almost no resupply. But as you breathe in oxygen, you're breathing something else out, and that part becomes dangerous even before the oxygen runs low. What happens when the air doesn't just get thin, it gets dirty with the thing your body is constantly dumping into it? Every day, each person exhales roughly 1 kilogram of carbon dioxide. Same 4-person crew, that's about 4 kilograms a day, more than a ton over a year if you let it pile up. On Earth, the atmosphere is so huge that our individual output just vanishes into it. In a sealed cabin with a few tens of cubic meters of air, levels rise fast. At around 0.5 to 1% CO2 by volume, you start getting headaches. You feel foggy, your ability to think clearly drops. Climb higher, and you get shortness of breath, faster heart rate, real distress. Push it far enough and CO2 doesn't just make you uncomfortable, it can knock you out and kill you, even while oxygen levels look okay. To keep that under control, spacecraft use scrubbers, systems that chemically grab CO2 out of the air. Materials like lithium hydroxide or amine beds react with CO2 and trap it. That works fine for short missions. You use a canister, it fills up, you throw it away and plug in a new one. On the International Space Station you can send up replacements. On a multi-year deep space run, there is no steady resupply. You can't afford a stack of one-time use canisters that weighs as much as the rest of the ship. You need systems that can be regenerated, CO2 captured, then released and vented or pushed into another loop day after day. So now you're juggling oxygen supply and CO2 removal, but you don't want separate one-way machines for everything. You try to close the loop, turn waste into input. That sounds elegant, but what does it actually mean inside a ship? Closed-loop life support is where you stop treating air and water as consumables and start treating them as part of an artificial ecosystem. You use electrolysis units to split water into hydrogen and oxygen, feeding fresh oxygen back into the cabin. You use catalytic reactors to process CO2, maybe converting it into oxygen and carbon monoxide, or into water and other compounds depending on the setup. You consider bringing plants or algae, bioregenerative modules that take CO2 and light and turn them into oxygen and food. Each of those subsystems has moving parts. Pumps push fluids, filters remove particles, membranes separate gases, catalysts sit in reactors and wear out over time. Everything draws power, everything has temperature limits, everything has failure modes, sensors that can lie, valves that can stick, seals that can crack. Put it all together and you're basically running a tiny, highly simplified version of Earth's biosphere and climate system, squeezed into a volume the size of a bus or a small house, with a crew that also has a dozen other jobs. If one part of that chain breaks and you're months from any possible help, you're on a timer. You might have backup systems, spare parts, manual procedures, but every fix eats into finite reserves. If the wrong combination goes down, You don't have a way to flush the air and start fresh. The system doesn't forgive, it just counts down, and that's just oxygen and CO2. In a closed metal can, the air is not just nitrogen and oxygen with a bit of carbon dioxide. What else is in there, building up quietly while you focus on the big numbers? Every material in your ship outgasses. Plastics release small amounts of chemicals, adhesives shed volatiles, lubricants can evaporate. On top of that, you're constantly adding biological material, skin flakes, hair, sweat, microbes from your body, particles from food. On Earth, all of this gets diluted into a huge atmosphere and usually vented outdoors. You rarely notice it. In a deep space habitat, there is no outside. The total volume of air is small. Volatile organic compounds can build up. The smell of plastic, cleaning products, cooked food, and human bodies all mix into a cocktail your lungs are stuck with. Small concentrations can cause headaches, eye irritation, throat irritation, or subtle long-term effects on organs, especially if you breathe them for years. To avoid that, you need additional filters and scrubbers targeted at trace contaminants, not just CO2. Activated charcoal, special chemical beds, microbial filters, all have to run, be changed, be monitored. You also need strict control over what materials you even allow inside the habitat, what paints, what glues, what fabrics, because every choice changes what ends up in your air. Humans are not just breathing the oxygen loop, they're also breathing the sum of every engineering decision, every manufacturing residue, every cleaning product used on a surface before launch. On multi-year missions, we don't fully know all the long-term health impacts of living inside that mix, and just when you think you've stabilized the chemistry, you hit the final ugly fact. All of this air is held in place by a thin shell of metal and composite. How stable is your atmosphere when a single fast-moving rock can poke a hole in it? Space is full of micrometeoroids, small bits of rock and metal, some only a few millimeters across, moving at speeds between about 20 and 70 kilometers per second, roughly 45,000 to 156,000 miles per hour. At those speeds, kinetic energy is huge. A grain that would just bounce off a car windshield on Earth can punch straight through multiple layers of spacecraft hull. If a particle hits and you're lucky, it just dents outer shielding. If you're unlucky, it makes a hole that connects your pressurized cabin to vacuum. Air doesn't trickle out politely, it starts escaping along the pressure gradient immediately. The rate depends on hole size and cabin volume, but the key point is simple. Your entire breathable environment now has a new path to leave and it will use it. You might have minutes, maybe hours to find the leak, isolate sections, throw patch kits onto the damage, and bring backup tanks online. During that time, pressure is dropping, alarms are sounding, and every decision you make is under stress. If the leak is in a place you can't reach or it splits into multiple paths, you may not be able to save the cabin at all. Your margin is thin. Every litre of air vented is mass you carried from Earth and ran through your systems, now gone. You can't open a window, you can't step outside, you can't breathe the outside environment. There is only inside and the vacuum pushing to become inside. So by the time you've kept oxygen flowing, CO2 under control, contaminants filtered, and the hull intact, you're already living at the edge of what a small crew can manage. And yet, there's another basic requirement you can't dodge, even if everything above works perfectly. The thing you drink, wash with, grow food with, and also uses radiation shielding, the heavy, irreplaceable substance that deep space barely has in usable form. How do you keep people alive when the thing they need most is also one of the heaviest things you can possibly launch, and space gives you almost none of it for free? Start with the basic number, your own daily water bill. Just for drinking, you use around 2 to 3 litres a day. Call it about half a gallon, but that is only the clean, obvious part. Real-life support has to cover drinking, food preparation, washing, brushing teeth, cleaning equipment, maybe a quick rinse after exercise. On current space missions, total use easily climbs into tens of litres per person per day, if you count everything that has water in it. You cannot afford that as pure use once and throw away. So you recycle, hard. You capture humidity from the air, you reclaim water from urine, You condense sweat. You recover water from the air you exhale. Good systems can hit 90 to 95% efficiency. That sounds impressive, but remember what the missing 5 to 10% means over time. If each person cycles through, say, 20 or 30 litres a day in total flows, and you lose just a couple of litres per day across a crew, that's hundreds of litres gone over months, thousands over years. Every litre lost is one more kilogram you should have launched. Over a 5-year mission, even small percentage losses add up to hundreds or thousands of kilograms of makeup water. That's extra mass, extra cost, and extra risk. So you don't just need recycling, you need recycling that stays very close to perfect for a very long time, with humans constantly pushing it. While you're fighting to keep enough water inside the loop, there's a weird twist. The same water that's painful to haul is also one of your best ways to stay alive against radiation. How do you reconcile the fact that your heaviest consumable is also one of your best shields? Water is very good at slowing down and stopping many kinds of radiation, especially charged particles like protons. Hydrogen atoms in water do a good job of absorbing energy from those particles through collisions. A thickness of water on the order of a few tens of centimeters can significantly cut down the number of damaging particles that reach you. That makes water a tempting material for building a storm shelter, a place in the ship where you surround the crew with tanks and get extra protection during solar events, but the numbers for real protection are not small. Wrap a habitat with a thick enough water layer, and you're adding many tons of mass. 1 metric ton is 1,000 kilograms, about 2,000 to 200 pounds. Now think in terms of dozens of tons of water for serious shielding, for example 20 or 30 tons. That's the mass of multiple small swimming pools, not counting the tank structures themselves. You have to launch that mass out of Earth's gravity well and then accelerate it for your deep space journey. In payload terms, that is the difference between a lean, tight ship and something that starts to look like a slow, heavy barge. So you compromise again. You cluster water tanks around your sleeping quarters or around a central panic room instead of everywhere. You accept more exposure in some areas to save mass. Once again, you are trading radiation risk against the brutal cost of moving kilograms. All of that water also has to stay in the loop somehow, and that loop does not run by itself. Turning sweat, urine, and cabin humidity back into clean drinking water takes work. What does that look like when you have no lakes, no rain, no backup supply at all? Recycling water is not just a simple filter in a bottle. You need pumps to move fluids through the system. You use filters to remove particles and microbes. You distill or use special membranes to separate pure water from dissolved salts and waste products. Some systems run at high pressure to force water through very fine membranes. Others use heat to boil and recondense it. Every step eats energy. On Earth, if the power goes out, you wait for repairs or use water from somewhere else. In deep space, if your power system dips or fails, recycling efficiency drops immediately. Maybe pumps slow down, maybe heaters don't reach the right temperature, maybe control systems fail to keep the whole process in balance. Your water plant is driven by the same power grid that runs life support, communication, and propulsion. If that grid wobbles, your clean water supply wobbles with it. There is no external reservoir to lean on, no underground aquifer, no glacier. The only input to the system is what you launched, plus what you might slowly mine from outside, and the only thing flowing through most days is your own waste. You're operating a small chemical and biological plant where the feedstock and the product are the same thing. Water your crew is going to drink, and that system never stays perfectly clean by itself. Closed water loops drift. What happens when the system you built to keep water safe slowly starts to contaminate it instead? Bacteria love moist, nutrient-rich environments. Pipes, tanks, and filters are perfect places for biofilms to form, slimy layers where microbes stick to surfaces and protect themselves. Membranes can foul, clogging with organic material and minerals. Filters can load up and lose efficiency. Sensors can drift out of calibration, telling you everything is fine when it's not. On Earth, you swap out a filter with a new one from the warehouse, flush the system, call a technician. In deep space, every spare part on that ship is one you chose before launch. Every filter, every membrane, every UV lamp, every pump seal is something you budgeted mass and volume for. If you didn't bring enough, or if something fails earlier than you expected, you can't call a supplier. A serious contamination event can spread through the loop. Bacteria in one tank can colonize another. Chemicals from a failed component can leak into water meant for drinking or for electrolysis. Fixing it might mean taking the whole system offline, running on minimal reserves and doing complex maintenance with limited tools. If you lose the battle, the result is simple. The crew no longer has safe water. That's not a minor inconvenience, that is a direct path to mission failure and death. So of course, people say, we'll just get water out there from asteroids or icy moons, space is full of it. There is ice out there, that part is true. But how do you actually turn a block of frozen rock in vacuum into drinkable water in a tank on your ship? Many asteroids and outer solar system moons contain vast amounts of water ice, trillions of tons easily. The problem isn't quantity, it's access. The ice is locked inside rock or dust, often at very low temperatures, and it's sitting in a vacuum. You don't just scoop it up and let it melt in a bucket. To harvest that water, you need mining equipment to break or drill the material, heaters or concentrated sunlight to warm it, systems to capture the vapor when the ice sublimates, and then equipment to cool, condense and purify it. All of that requires hardware, structures, robots or crews, and a lot of energy. It also takes time, likely months or years of steady operation to build up large reserves. For a small cruise ship on a deep space trajectory, we'll just mine water along the way, is basically a fantasy with current tech. It's like someone stranded in a life raft in the middle of the ocean saying, I'll just build a full desalination plant from scratch. In theory, yes, the raw material is there. In practice, you don't have the mass, the power, or the time to make it work on the scale you need. So water, the thing you absolutely cannot live without for more than a few days, is heavy to launch, complex to recycle, risky to protect from contamination, and hard to replace out there. You're walking a tight line where losing a few % efficiency here or a filter there can push your entire mission into the red. And even if you somehow keep that loop running, even if you never run dry, your body still needs something you can't distill out of waste. Not fully the constant stream of energy and nutrients that keeps your cells alive. In deep space, how do you feed a crew for years when there is nothing to hunt, nowhere to farm, and no backup supermarket to supply ship away? You can close the loop on air and water, but how do you close the loop on food when space gives you exactly 0 calories back? Your body doesn't care that you're in deep space, it still burns energy like it's on Earth. Most adults run somewhere between 2,000 and 3,000 kilocalories per day. More if you're stressed, working hard, or doing long exercise sessions to fight muscle and bone loss. Take a middle value, say 2,500 kilocalories per person per day. For a crew of 4, that's about 10,000 kilocalories every single day, whether you're in orbit, on the way to Mars, or halfway to nowhere. Stretch that over 5 years. 10,000 kilocalories per day times about 1,825 days lands you in the ballpark of 18 million kilocalories. Even if you stick to the simpler 14 million kilocalories estimate for conservative planning, the mass is still serious. If each kilogram of dry food stores around 4,000 kilocalories, you're looking at roughly 3,500 kilograms of food, over 7,700 pounds, before you even count packaging, extra reserves, or any safety margin for higher activity levels. That's basically a small car's worth of mass whose only job is to stop you from starving. And remember, it's not just mass, it's volume, storage system, thermal control so it doesn't bake or freeze, and inventory tracking so you don't find out in year 4 that you miscounted. You can't just decide halfway through the mission to eat out or get a delivery. Once you launch, your calorie budget is locked in. But food isn't just about raw calories, it's about nutrients, vitamins, and long-term health. Even if you somehow pack enough kilograms to hit the energy numbers, what happens to the quality of that food after years in a radiation bath? Vitamins and delicate nutrients don't like time, heat, or radiation. On Earth, long storage slowly degrades them. In deep space, you add ionizing radiation to the mix, particles that can break chemical bonds in the food just as easily as in your DNA. Even in sealed packaging, the molecules inside can get rearranged or damaged. So that carefully balanced diet you loaded at launch, with the right mix of vitamins A, C, D, B complex and all the rest, slowly drifts. After a year or two, the label on the package no longer matches what's actually inside. Vitamin C might be down, some fats might be oxidized, flavor changes, texture changes, and nutrient density slides. On a short mission, you can ignore that drift. On a 5-year run, it becomes a real question. Will my diet still be balanced in year 3, or am I quietly sliding into deficiencies while thinking I'm fine? Long-term lack of key vitamins doesn't just make you a bit tired, it can damage your immune system, your bones, your blood, your nervous system. You can't see that coming day to day. It shows up slowly, exactly when you're farthest from help. So maybe you decide not to rely only on stored food. You add the obvious fix. You grow some of it on board, fresh plants, maybe even animals one day. That sounds simple when you say it, but what does farming actually look like when there is no gravity and no open field? In microgravity, soil doesn't behave like soil. On Earth, gravity pulls water down, air bubbles up, roots grow downward following both gravity and chemical gradients. In space, water forms floating blobs or clings to surfaces, air doesn't rise, and roots don't have a clear down direction. Traditional pots just turn into weird, half-flooded containers with pockets of air and water in the wrong places. So you switch to controlled systems, hydroponics or aeroponics, where roots hang in nutrient solutions or are sprayed with nutrient mist. You provide artificial lighting, usually LEDs tuned to specific wavelengths. You mix nutrient solutions at precise concentrations, and you control temperature, humidity and carbon dioxide levels. Now your clean mechanical spacecraft has a greenhouse section with warm, humid air, wet surfaces and organic material everywhere. That greenhouse isn't just full of plants, it becomes a home for insects, molds, bacteria and plant pathogens unless you maintain it perfectly. Pests that are annoying on Earth, where you can spray fields or burn a crop and replant, become dangerous when your field is a few square meters and represents a big chunk of your fresh food. One outbreak of the wrong fungus, one insect species that gets out of control, and a large part of your food growing capacity can vanish. And even if you keep obvious pests under control, there is another risk. The biology itself doesn't behave exactly like it does on Earth. How safe is it to bet your life on organisms that haven't evolved for microgravity? Experiments on the International Space Station and other platforms show that plants, microbes and small animals all change behavior in low G. Growth patterns shift, root structures look different, gene expression can change, biofilms, those slimy layers of microbes on surfaces, can form faster or in different ways. Some bacteria become more virulent, some plants handle stress differently. If your entire food supply or a big fraction of it comes from living systems in that environment, you are basically running a biological experiment where you are the test subject. You might discover that a certain plant variety that thrived in Earth tests suddenly struggles, or that your chosen microbe for recycling nutrients behaves unpredictably after a year in space. One day you might walk into the greenhouse and find a major crop covered in mold, or a nutrient cycle stuck because the microbes you rely on have formed a thick, resistant biofilm in the wrong place. On Earth, you would switch suppliers, plant a different variety, bring in a new culture. In deep space, you only have what you brought, plus whatever mutated out there with you. And here's the final harsh part of the food problem. On Earth, agriculture failures are buffered by a whole planet. In deep space, your ecosystem is as big as your ship, and that's it. What happens when that small system takes a hit? On Earth, if one region has a bad harvest, food can be imported from another region. Global trade and large ecosystems smooth out local disasters. If a fungus wipes out a field, it's a crisis for that farmer, but not for the species as a whole. In deep space, you don't have that safety net. Your food sources are whatever you stored, plus whatever you grow in a tiny sealed environment. That means your entire food security rests on a few rooms of hardware and biology. A single design flaw in your hydroponic system, a single miscalculation in nutrient mix, a single disease that hits your main crop could wipe out a huge fraction of your calories. There is no second greenhouse on another continent. There is no cargo ship full of grain coming over the horizon. If you hit that situation far from Earth, your choices are narrow and brutal. Ration what's left, hope stored food can stretch far enough, and accept long-term health damage from nutrient shortfalls, or watch the mission fail outright as you simply run out of energy to run your own bodies. So by the time you've packed and grown enough food to keep cells firing, you've added yet another big, fragile subsystem to a ship that already has too many. And every one of those systems, air, water, food, has one thing in common. They all eat power. In deep space, every breath, every sip, every bite is paid for in watts. And the further you go from the sun, the harder it gets to generate those watts at all. How do you keep all of this running when space gives you no power outlet? And the further you go, the weaker your only free energy source becomes. Near Earth, the sun feels generous. At about 1 astronomical unit, the energy hitting a surface pointed straight at the sun is around 1,361 watts per square meter. That's your baseline. Build solar panels, point them correctly, and you get a decent power budget. But the key detail is this: that number drops fast with distance. Double the distance to 2 astronomical units, and you're down to roughly 340 watts per square meter, about 1/4. Go to 5 astronomical units out near Jupiter, and you're around 54 watts per square meter. You didn't just lose a bit, you lost more than 90%. To keep the same power output at 5 astronomical units that you had at Earth, your solar array area has to grow by roughly a factor of 25. That means panels that are absurdly huge, with more structure, more mass, more points of failure, and more surface for micrometeoroids to chew on. And that's in perfect sun, no shadow, no dust on the panels, no misalignment. In reality, you get eclipses behind planets, slight pointing errors, degradation over time, and damage. So as you head into deep space, your solar-based power budget collapses unless you're willing to drag around gigantic, fragile wings. That's why, beyond a certain distance, you're forced toward a different answer. One that doesn't care how far you are from the sun, but comes with its own heavy baggage, a nuclear reactor. Nuclear power sounds like the clean fix. A compact reactor can deliver hundreds of kilowatts continuously, day and night, at any distance from the sun. In pure numbers, that's far more attractive than stretching solar panels until your ship looks like a flying field. But you're not just adding a power box, you're importing an entire power plant into your spacecraft. You need the reactor core with its fuel, control rods or other control system, primary coolant loops, secondary loops, pumps, monitoring systems, and a large radiator field to dump the waste heat. You also need shielding to protect the crew from neutron and gamma radiation, which means thick slabs of dense material, more mass. Put it all together and the system easily weighs many thousands of pounds, several tons in metric. And it's not like swapping a battery pack when something goes wrong. Maintenance on a nuclear core in deep space is a serious engineering nightmare. Getting near the core is dangerous. Opening it is basically impossible for a small crew, and you cannot shut it down and call a technician. If the control system misbehaves, if the cooling system fails, the consequences range from a dead reactor that leaves you without power to a damaged reactor that is both dead and still radioactive. So nuclear solves the distance problem, but it adds complexity and high consequence failure modes. And even if generation works, you still need a buffer. Power needs don't sit at a flat line, they spike and dip. That's where you think, we'll just store extra in batteries. The problem is, chemistry doesn't let you cheat very far. Chemical batteries, even advanced types, have limited energy density. You might get a few hundred watt-hours per kilogram, say 200 to 300 watt-hours per kilogram for realistic rugged systems. If you want to store a megawatt-hour of energy, enough to run a small town for about an hour, you're looking at several tons of batteries, easily. In metric, that's thousands of kilograms of cells. In imperial, that's many thousands of pounds. You cannot reasonably stockpile months of power in batteries on a deep spaceship. The mass would crush your launch budget. At best, you store enough to smooth short-term fluctuations and cover brief outages, maybe hours, not weeks. Fuel cells have similar constraints. They just shift the problem to storing reactants, which also have mass and volume. The result is that your power system has to keep generating energy almost continuously, with only a thin buffer against interruptions. If the reactor trips or the solar arrays go offline, you're running on limited reserves. You don't have a huge backup tank of electricity. When the generators slow down, your ship's life starts shrinking to the remaining hours on those batteries. And every subsystem you've built, every piece of life support and comfort we've talked about, is sitting on top of that fragile power stream, drawing watts. What happens when that stream falters? Everything you need to stay alive eats power. Life support pulls watts for pumps, fans, compressors, and scrubbers. Heating and cooling pull watts to move heat around your habitat and into radiators. Communication gear needs power to talk to Earth over hundreds of millions of kilometers, especially if you want high data rates. Navigation and guidance systems, radar, cameras, and computers all add to the load. Hydroponic lights for growing food are intense power users, often running at hundreds of watts per square meter. Robotics, sample handling, any onboard manufacturing or repair tools, they all go on the same bill. When generation drops, you don't have the luxury of keeping everything on. You start making choices, and those choices are ugly. Do you dim or turn off the grow lights, risking your food supply to keep communications and navigation at full capacity? Do you cut back on heating, letting parts of the ship cool toward dangerous levels to keep life support gases moving? On Earth, power grids have multiple plants, backup lines, neighbouring regions to borrow from. In deep space, your generator is alone. If it stops, or if it's damaged, there is no external grid to lean on. The line between essential and optional systems moves around under stress. You might think certain experiments or comforts are always expendable, until a failure in one part of the ship makes them necessary for a workaround. The more tightly packed and multi-use your systems are, the harder these decisions get. And every decision is made with the knowledge that if you get it wrong, people die. Even if you solve generation and manage the load perfectly, energy hits you from the other side too, as heat. Every single watt you generate ends up as heat somewhere. You're not just fighting to get enough power, you're also fighting to get rid of the waste. In a closed spacecraft, there is no air outside to carry heat away, only radiation. Your radiators, those big panels facing cold space, are your only way to dump excess energy. The more power you generate and use, the more heat your radiators have to emit as infrared light. If your power system can output, say, hundreds of kilowatts, your radiator field has to be sized to handle that much waste. Heat under worst-case conditions. If you undersize the radiators, or if some panels get damaged by micrometeoroids, or covered in dust, or shadowed by other structures, your ability to dump heat drops. But your systems are still running, making more heat. Temperatures inside the ship start to creep up. Electronics get hotter, failure rates increase, lubricants break down faster, humans become uncomfortable, then unsafe. It's a slow oven problem. The whole ship warms gradually, and you can't just crack a window. If you oversize the radiators to be safe, you pay in mass and vulnerable area. More panels mean more structure, more risk of impact damage, more joints, more things that can leak or break, and they still have to survive extreme temperature swings themselves, heating one side and cooling the other over and over as your orientation changes. So energy in deep space is a double bind. You need enough generation to run life support, propulsion, communication, and everything else, but every bit of that energy has to be carried, controlled, and then dumped as heat through a limited radiator area. Too little power, your systems starve. Too much without enough cooling, your ship slowly cooks. All of this is happening while you're moving through an environment where distance itself is another enemy. Because the moment you leave the neighborhood of Earth, you also lose the luxury of quick rescue, easy resupply, and real-time help. Beyond a certain point, Even if every system you built is perfect, the sheer scale of space turns every failure into a one-way problem. How do you run a mission when far away stops meaning hours or days, and starts meaning no one can ever get to you in time? Even near Mars, basic communication stops feeling normal. Radio waves move at light speed, but light speed is not infinite. At typical Mars distances, a signal takes between about 4 and 24 minutes one way. That means a round trip you ask a question and wait for an answer can take close to an hour. Go farther into the outer solar system, and that lag stretches to many hours. There is no real-time call for tech support, no live voice on the other end walking you through a procedure. So every serious problem has to be solved locally by you, with the tools and knowledge you brought before launch. Ground control can send suggestions, videos, patches, but you will always be acting on old information. In a fast-moving emergency, waiting 10, 20, 30 minutes for a response is the same as having no response at all. The only control room that actually matters is inside the ship. So you might think, if things really get bad, just turn around and come home. But in deep space, turning around is not a casual decision, because changing your speed is expensive in the most brutal way physics knows. To change your velocity in space, you burn propellant and throw it out the back of your ship. The relation between how fast you can end up moving and how much propellant you carry is described by the rocket equation. You don't need the math, just the shape of it. Each extra kilometre per second of speed you want to add or subtract costs you exponentially more propellant. That means your fuel mass grows very fast for even modest increases in required speed change, what we call delta V. A serious deep space mission might need total delta V in the tens of kilometers per second when you add up all the burns, leaving Earth, adjusting your course, braking near your destination, maybe entering orbit, then leaving again. Now stack that delta V requirement on top of a vehicle that also has to carry tens or hundreds of tons of life support structure, water, food, shielding, and power systems. The result is a ship whose total mass starts to look like a small skyscraper lying on its side. Every kilogram of extra fuel for safety makes the ship heavier, which then requires even more fuel to move. You quickly hit a wall where you cannot practically carry enough propellant to both complete the mission and keep a large reserve for big course changes. You are locked into a narrow budget. Once you choose a trajectory and commit the burns, your ability to just stop and go back is physically limited, not just financially. If you can't easily slam on the brakes, maybe you lean on resupply instead. On the ISS, cargo ships show up every few months bringing food, water, oxygen, spare parts. Why not do that halfway to Jupiter? Because meeting a moving ship in deep space is not like dropping a package from a plane. It's a planetary scale logistics problem. To send even a small crate of critical parts to a ship on an interplanetary trajectory, you need to line up launch windows, transfer orbits, and rendezvous timing years in advance. The resupply vehicle has to leave Earth at exactly the right time, follow its own precise path, and arrive at the exact point in space where your ship will be, moving at many kilometers per second. A tiny navigation error at launch can grow into a massive missed distance months later. If the trajectories don't match closely enough, your resupply doesn't arrive late, it just flies past at several kilometers per second and is gone forever. There's no way to hit the brakes and reverse to go grab it. So you can't treat resupply as a flexible backup plan. It's more like aligning two bullets in flight so they gently bump. That leads to the next issue. If you can't count on quick resupply and you can't afford huge fuel margins, what happens when you want to abort the mission? Apollo missions had built-in abort modes. On the way to the moon, many trajectories were arranged so that if something went wrong, the spacecraft could swing around the moon and return to Earth in a matter of days with relatively small course corrections. Earth was always a short hot burn away. On a deep space mission, once you've done the main burn and are coasting toward the outer system, the energy you've already put into your trajectory is enormous. Changing that path significantly, enough to turn it into a quick return, would require a huge amount of delta V. With realistic fuel loads, that usually isn't available. Your engines can tweak your course, but they can't undo the fundamental fact that you are already falling along a path set by your initial burns and the gravity of the sun and planets. If something goes fundamentally wrong halfway to, say, Saturn, life support damage, reactor failure, serious structural issue, your options are limited to stabilizing what you have and riding it out. There is no powerful abort button that bends your arc back to Earth in a few days. You might be months or years away from any possible close pass to a body where you could even attempt a landing or aerobraking. When you commit to a deep trajectory, you commit to living with it, for better or worse. And even before anything fails, the crew feels that reality. Distance isn't just a number on a screen, it's a psychological weight. What does that do to people, day after day, when they know in plain terms that nobody is coming? At a distance of 1 billion kilometers, more than 600 million miles, Earth is just a bright star. You know that any conversation with home is delayed by well over an hour round trip. You know that even if the entire planet wanted to launch a rescue, the timing, fuel and trajectory problems make it effectively impossible during your mission window. That knowledge doesn't sit in the background. It shapes how you think. Every decision you make, every maintenance task, every deviation from procedure carries extra pressure. Mistakes are not fix it next shift. They are hope this doesn't strand us with an unrepairable system 6 months from now. Humans evolved in groups with backup nearby, another family, another village, another region. If your camp burned, you could walk somewhere else. In deep space, there is no somewhere else. Your world is the hull, and beyond that is vacuum. Morale becomes fragile in a different way. Conflicts inside the crew are not just awkward, they're inescapable. Stress from technical problems stacks on top of the constant background awareness that failure has no safety net. Some people might adapt, some might even thrive under that weight, but you can't assume everyone will. And if one person cracks, that stress spreads to everyone else in the small, sealed environment. So distance in deep space isn't just extra travel time, it's a hard barrier that turns every technical risk into a sharper, more final threat. You're operating at the end of a very long, very thin supply chain, with no real-time help and no physical backup. And while you're that far out, locked into a trajectory you can't easily change, with no one able to reach you and no way to pull over, space has one more layer of hostility to throw at you. Countless tiny, fast-moving pieces of debris and dust that you often can't see, can't dodge, and can't fully armor against, any one of which can turn your ship from barely survivable to suddenly gone. How safe can a metal shell really be when a grain of sand can hit it harder than a rifle bullet, and you can't even see it coming? Out in deep space, dust is not soft. A tiny grain about 1 millimeter across can be moving at 20 kilometers per second, roughly 45,000 miles per hour, sometimes faster. The brutal part is that impact energy scales with velocity squared. So if you double the speed, the energy doesn't just double, it goes up by a factor of 4. That 1 millimeter particle at those speeds carries enough punch to go through metal that would shrug off a bullet on Earth. When it hits your ship, you don't get a slow crunch, you get a micro-explosion. The grain vaporizes, parts of your hull vaporize, and a shockwave runs through the structure. If it hits a thin line, a radiator tube, or a vulnerable corner of a module, you're looking at punctures, leaks, or broken components from something you'd never notice in your hand, and there are no weather reports for this. You don't see a storm of grains on the horizon. The first sign may be an alarm saying pressure is dropping or a solar panel string going dead. That's just one particle. Space isn't sending you one, it's sending you many over and over for years. So even if you dodge the worst of those high-energy hits, what about the constant low-level barrage that never stops day after day? A lot of micrometeoroids are too small to punch all the way through, but they still slam into exposed surfaces and leave pits and craters. Over a few days, that's just interesting. Over years or decades, it becomes erosion. Solar panels lose their smooth, clean surfaces. Radiator fins get peppered. Optical sensors get scratched. Reflective coatings that are supposed to bounce sunlight or radiate heat start to darken and peel. That slow damage directly hits your performance. Solar panels produce less power. Radiators dump less heat, making thermal control harder. Structural elements weakened by millions of microcraters become more vulnerable to bigger impacts or to stress from temperature swings. This isn't cosmetic wear. It's your power budget and cooling margin being eaten away by invisible sandblasting. On Earth, you might shut down a worn-out machine and replace it. In deep space, the thing being worn away is the only ship you have. Maintenance becomes a race against the background erosion of the environment. So you respond the obvious way, you add armor. You wrap your ship in shielding to take the hits first. That helps, but what does that really cost you? Modern spacecraft use multi-layer systems called Whipple shields. The idea is simple: put a thin bumper layer out in front of your main hull. When a fast particle hits that first layer, it shatters and vaporizes, spreading out the impact into a cloud of slower fragments and plasma. That cloud then hits additional layers and the main wall. By the time it gets to the pressure shell, the damage is spread out and often absorbed safely. It works, but it needs material. Each square meter of hull might get several layers of metal and fabric, adding up to kilograms per square meter. Multiply that by the entire external surface area of a large deep spaceship, with habitats, tanks, trusses, solar arrays and radiators, and the total quickly reaches tens of tons of extra mass. Once again, every kilogram of shield is a kilogram you can't use for something else, like extra water, more food, stronger engines, or more crew. You're turning your ship into armor, and the more you do that, the harder it is to push that ship anywhere. You can't just keep stacking protection until you feel emotionally safe. Physics sends you a bill in propellant and cost. And while you're focused on shielding against external hits, there's a quieter, more annoying threat building up on the inside, debris you created yourself. Inside the ship, microgravity changes how junk behaves. A loose screw doesn't fall to the floor. Flakes of paint, tiny fibers from clothing, crumbs of food, fragments from 3D printing or repairs, all of that just floats. Every time you bump something, open a panel or move equipment, you can release more small pieces into the air. Some of that gets pulled into air filters, where it builds up and needs to be cleaned. But not all of it. Particles can drift into vents, lodge in valve seats, get into pump mechanisms, scratch rubber seals, and settle in places you never wanted them. In a closed system that runs for years, your own ship becomes a source of contamination and mechanical wear. You can't just bring out a regular vacuum cleaner and let gravity help. Cleaning in microgravity is a disciplined, continuous task. You'll have to track down where debris is coming from, change procedures to reduce loose fragments, and design hardware so it sheds less material. Even then, the problem never goes away fully. It's like dealing with dust, but the dust can break hardware, and it never actually settles, so you're fighting tiny threats from outside and inside at the same time. And even if you stay on top of the constant barrage, there's a more uncomfortable question sitting in the background. What about the one big piece, the rare fragment that you'll probably never meet, but absolutely cannot survive if you do? Most of space is empty, and the odds of a large chunk of rock or metal hitting a single ship are low. But low is not zero, especially when mission durations stretch into years or decades. A fragment just a few centimeters across, moving at tens of kilometers per second, carries enough energy to rip through multiple layers of shielding and structure and keep going. If that impact intersects a critical area like a main propellant tank, a reactor module, or the core habitat, it can be instantly fatal to the mission. You could try to armor against that level of threat, but the required thickness and strength push you into absurd territory. You'd end up with something closer to a flying bunker, with walls so thick and massive that getting it off Earth, and then accelerating it interplanetary speeds, would be nearly impossible with current or near-term rockets. Protecting perfectly against every possible impact isn't realistic. You accept some level of residual risk. So the reality is, over very long times, the chance that your ship takes a truly catastrophic hit creeps upward. You might beat the odds and never meet that kill shot, or you might be unlucky. There's no warning radar for millimeter dust clouds, no straightforward way to dodge a pebble you didn't know was there. moving at tens of kilometers per second. And all of this, every grain and chip and fragment threatening your hull, is happening while your mind is trying to operate in a setting with no sunrise, no natural rhythm, no open skier, and a constant awareness that one thin barrier is all that separates you from instant death. How stable can your mind really stay when your world is a metal tube, your sky is a ceiling panel, and there is no such thing as going outside for a bit? Your body runs on cycles, roughly 24-hour rhythms tuned by billions of years of living on a spinning planet. Light goes up, temperature shifts, your brain releases hormones, your core temperature changes, you get sleepy, you wake up. In deep space, none of that is built into the environment. There is no sunrise, no sunset, no natural temperature swing, just whatever pattern you impose with lamps and heaters. If that pattern slips, even as a little, you pay for it. Lights staying bright too long, shift work that jumps around, inconsistent nights for different crew, all of that can scramble your circadian system. Melatonin, the hormone that signals night to your body, stops lining up with sleep. Cortisol, your stress hormone, spikes at the wrong times. You get insomnia, or you fall asleep at the wrong hours, or your sleep becomes shallow and broken. Sleep debt in deep space is not just feeling tired. It hits memory, reaction time, problem solving, emotional control. You're trying to run a complex life support machine while your brain's internal clock is desynced from whatever schedule the ship is on. It's like running an operating system without a clean clock signal. Everything still works, but it jitters, lags and glitches at the worst moments. And that's before you factor in the human side, the fact that your entire sensory world becomes narrow and repetitive. How does your brain handle months and years of almost nothing new? In a deep space habitat, your environment is the same modules, the same walls, the same faces, every day. The view out the window, if you even have one, barely changes, just stars and dark. You can rotate pictures on a display, play videos, simulate a forest on a screen, but your senses know the difference between pixels and real variation in air, smell, sound, and light. We already see what long isolation does in places like submarines and Antarctic stations. Even with Earth right there, people show increased rates of depression, anxiety, and irritability after long tours. They can still step outside sometimes, feel real wind, see a horizon, and it still hits them hard. In deep space, that outlet doesn't exist. There is no fresh air break, no real horizon, no new town, no random strangers. The only new stimuli are the ones you brought with you on a hard drive. Over years, that sameness wears you down. Small annoyances feel bigger. Motivation drops. You start to feel like the mission is your entire life, not a phase of it. And on top of that monotony, your brain is tracking something else in the background, constant risk. How calm can you stay when you know, at all times, that only a few centimeters of metal and composite are between you and vacuum? Every sound, every creak in the hull, every status chirp from a sensor carries extra weight. A minor alarm about a pump or a pressure threshold isn't just maintenance time, it's, is this the thing that kills us 6 months from now if we don't handle it perfectly? Radiation alerts, solar flare warnings, micrometeoroid impact logs, all stack into a picture where the ship feels like a fragile platform in an environment that wants it gone. Your body reacts to that, low-level stress becomes continuous, cortisol stays elevated, heart rate patterns change, sleep gets lighter and more easily disturbed. Chronic stress damages health, suppresses immune function, and pushes people toward irritability and impulsive decisions. Over years, that isn't a mood, it's a slow form of trauma, built from thousands of small that could have been bad moments. And you're not dealing with that alone. You're trapped with a handful of other people who are going through the same thing. What happens when normal human conflict hits a place where nobody can leave? Humans argue even in paradise. Misunderstandings, different working styles, leadership disagreements, all of that happens in any group. On Earth, if a team dynamic breaks down, people transfer, quit, move cities, or at least go home at night. In a deep space capsule or habitat with 4 to 10 people, there is nowhere to go. Your living space, your workplace, and your social circle are the same physical few rooms. If two crew members stop trusting each other, they still share air. If the commander makes a bad call, you still need that person to sign off on repair plans. If a pair of people build up a private grudge, it can split the team into sides. Your HR department is literally the same few people you're angry with. There is no neutral outside mediator, no third-party support, unless you count messages delayed by tens of minutes from Earth. Social breakdown in that context isn't just awkward. It can compromise checklists, sabotage cooperation during emergencies, slow down repairs, and push stressed people into taking shortcuts. A crew that stops talking honestly is as dangerous as a failing pump, because critical information stops flowing just when you need it most. Layer on top of that a deeper, quieter pressure, the awareness that your life is completely cut off from the natural environments your brain expects. What does that do to a human sense of meaning? Your ancestors lived under open skies with weather, trees, animals, and other humans visible in all directions. Even modern city life puts you in touch with seasons, crowds, landscapes, and a constant background of living systems. In deep space, there is none of that. There is no wind, no rain, no birds or insects, no street noise, no distant mountain. There is the hum of fans, the buzz of electronics, and numbers on screens telling you that you're moving at tens of kilometers per second through vacuum. Some people might love the raw awe of that, the clean focus of a mission, the sense of doing something historic. Others will feel something else growing over time, a kind of emptiness or vertigo when they really absorb how far they are from any natural environment, from any unengineered place where humans can exist without machines. That can turn into existential stress. Questions like, what am I doing out here? Or does this risk make sense? Hitting at 300 ship time when you're already short on sleep. If that coincides with technical problems, crew conflict, or health issues, it magnifies them. A mind that's starting to crack under isolation is not the mind you want making decisions when life support throws a fault code. So deep space doesn't just attack your lungs, your bones, and your electronics. It attacks your time sense, your mood, your stress systems, and your basic need for a healthy, varied social and natural environment. You can fake day and night, you can run crew psychology protocols, you can screen people as hard as you want, but you're still running human brains in settings they never evolved to handle. And if you're thinking, we'll grow a new kind of human for this, people who are adapted to it, people born and raised in space, that sounds like a solution, until you realize that turns the mission into something even more extreme, a multi-generation biology experiment where the lab is the ship, and the subjects are the future of our species. How do you plan for humans in deep space forever, when you don't even know what happens if a single human pregnancy runs from start to finish out there? Right now, no human has ever been conceived, grown, and born in space. All astronauts were conceived on Earth, developed in a 1G womb, and grew up under normal gravity in Earth's environment. The data we do have comes from animals, and it's not comforting. Experiments with fish, rodents, and other species in microgravity show changes in how embryos develop, shifts in gene expression, problems in bone formation, and oddities in organ development. Some of those changes might be minor, some might be serious, and we don't fully understand which is which. If you decide to build a multi-generation deep space population, you're not just moving a crew, you're starting a biology experiment. There's no parallel population growing up in a perfectly matched Earth environment to compare against. On top of that, you're stacking radiation on the most sensitive cells you have, the germ cells that carry genetic information to the next generation. Sperm and eggs are not shielded by being inside a body. They're vulnerable to the same ionizing radiation that hits everything else. On Earth, in high radiation environments, we already see measurable increases in birth defects and cancer rates over time. Deep space is harsher than any natural place we live right now. Increased mutation rates in germ cells mean that some fraction of conceptions will carry extra genetic errors. Many of those errors will be harmless, some will be neutral, and some will be harmful or lethal. When your entire population is small to begin with, every extra failure hits harder. You're not just risking individuals, you're risking the stability of the whole community. Even if you somehow manage radiation and microgravity well enough that embryos can survive and be born, you still have the physical development problem. Adults in microgravity lose 1 to 2% of bone mass per month in key regions, even with heavy exercise. You could end up with a lineage that is physically trapped in low-gravity habitats. Their home stops being Earth or any Earth-like planet and becomes the ship or station itself. Going home, in the sense we think about it now, might not be physically possible for them. And while all of this is happening at the level of individual biology, there is a quieter, slower risk building at the genetic level of the whole group. A deep space habitat holds a small number of people. That means a small genetic pool. On Earth, billions of people mix genes across continents. Even small towns are connected by travel, migration, and relationships that bring in diversity. That mixing helps dilute harmful mutations and keeps many inherited diseases rare. In a ship or a small deep space colony, your population might be in the tens, maybe hundreds if you're ambitious. That's more like an isolated village than a planet. With a closed genetic pool, relatives are more closely related than you might like, and over generations that increases the chance that harmful recessive traits meet up. You can try to manage this with genetic screening, strict population planning, even stored gametes from Earth. But all of that needs technology, storage, and careful control over many decades. Any failure in those systems, or any social breakdown in how they're used, can let inherited problems spread through a population that has nowhere else to pull fresh genes from. Step back from the technical details and you hit the biggest problem of all, ethics. To truly survive in deep space, not just visit and come back, humans would need to live and die there across many generations. You're not just testing hardware anymore, you're testing the entire human life cycle in conditions this species never evolved for. There is no ethical way to prototype that at full scale. You can't fully simulate 50 or 100 years of life in deep space on Earth. You can't get complete answers from animal models and short missions. At some point, to really find out what happens, you'd be committing real people and their descendants to live out the experiment from the inside. So long-term human biology in deep space isn't just a bit more radiation or a bit more gym time. It's a stack of unknowns about growth, genetics, and health that only show themselves over decades. You'd be asking future generations to pay the biological price for choices made by a small group at the start. And all of that is layered on top of machines that also don't last forever. Even if humans could somehow adapt, the hardware they depend on is quietly breaking down, atom by atom, joint by joint, in an environment that destroys materials in ways we still don't fully control. While your biology drifts away from the Earth baseline, your ship is also slowly being eaten by vacuum, radiation, and time. How long can a starship really last when the vacuum outside is quietly destroying every material choice you made? Day after day, even while the systems look fine on your status screen. Near Earth, in low orbit, you deal with atomic oxygen, individual oxygen atoms slamming into surfaces at high speeds. They strip away thin layers of material, especially plastics and coatings, so engineers already have to think about surface chemistry carefully. Go out into deep space and the atomic oxygen drops, but a different set of problems steps up. Intense ultraviolet light from the sun, plus high-energy particles from cosmic rays and solar storms, start breaking chemical bonds in polymers, paints, and sealants. A cable jacket that looked tough on launch day slowly becomes brittle. A soft rubber seal slowly loses its flexibility, fine cracks creeping in where you can't see them. Thermal blankets designed to protect you from heat and cold can flake, their outer layers breaking down under radiation and UV. Over a few months, you might not notice much. Over years, you can end up with materials that were rated space grade in tests on Earth, but now behave more like dried out plastic in an old car. So the ship that launched as a solid, tightly sealed machine is aging, not just in obvious ways like dents and scratches, but at the molecular level, and that's just from the environment. The materials themselves are also changing from the inside out. Most materials have gases trapped in them when they're manufactured. In vacuum, those trapped gases slowly leak out, a process called gassing. It's why new spacecraft sometimes fog optics or sensors if designers don't control material choices. Over time, as outgassing continues, properties of those materials can drift. Polymers can shrink slightly or change stiffness. Adhesives can weaken. Even metals, under repeated stress from temperature swings and mechanical loads, can develop micro cracks. Then there's creep, the slow, permanent deformation of materials under stress. Polymers under constant tension can stretch very slowly. Metals under cyclic loads, like parts that heat and cool every orbit, or supports that flex slightly with spin, can accumulate fatigue damage. On a mission that lasts a few years, you might catch these problems early. On a mission that's supposed to last decades, every bolt, weld and gasket is aging in conditions no long-term Earth test fully duplicates. You're guessing how a structure built for 10 or 15 years will behave in year 30. All of this is happening even before you talk about moving parts, the places where you deliberately asked materials to rub against each other in vacuum and still behave. Ordinary oils and greases that work fine in cars and aircraft don't survive in vacuum. They evaporate or break down, leaving residues that can gum up mechanisms. So space hardware uses special lubricants, very stable oils, greases tailored for vacuum, or even solid lubricants like molybdenum, disulfide, or certain coatings. These give you working hinges, latches, bearings, and actuators, but even they have limits. Every moving part on your ship, an airlock hatch, a robotic arm joint, a pump shaft, a valve stem, has a finite number of cycles before wear builds up past the safe point. In low Earth orbit, you can design for a certain mission length, then retire or overhaul the hardware. In deep space, if your mission is supposed to span decades, you may hit the cycle limits of some mechanisms while you still need them every day. An airlock latch that was good for 10,000 open-close cycles might be fine for an ISS module, but on a long, deep space mission with constant maintenance outside, you can approach that number. A pump that was sized for a certain number of start-stop operations might fail earlier if environmental conditions were harsher than expected. If the wrong mechanism runs out of life, you lose more than convenience. You can lose whole capabilities. So you push back with design, you add backups, you add redundancy, you bring spare parts. But every time you add a backup, you're also adding weight and giving yourself more systems that can fail in new ways. Redundancy sounds simple, just bring 2 of everything. In reality, you're layering complexity. 2 pumps mean more valves, more control logic, more wiring. 3 computers in a voting system give you better tolerance against 1 bad unit. But now you have more boards that can fail from radiation or aging. Spare parts need storage, labeling, inventory management, and people who remember how to install them under stress. Every extra kilogram of redundancy is a kilogram you have to lift from Earth and accelerate into deep space. Every extra subsystem increases the number of interactions that might misbehave. The more intricate your ship, the more potential failure combinations you have to think about. You're trying to armor yourself against entropy by adding more structure, but that extra structure gives entropy more targets. On Earth, when complexity and wear catch up with a machine, you can take it out of service and do heavy maintenance in a proper facility. How do you do that when your facility is just the interior of the same aging ship you're trying to save? Ships go into dry dock, airplanes go into hangars for deep inspections, bridges get crews, cranes, and months of work. In deep space, none of that exists. Your dry dock is whatever tools, scaffolds, and replacement parts you packed before you left. Major repairs might mean rotating or translating the entire vehicle to get at the right surface, then sending crew out in suits to cut, weld, and bolt in a vacuum, with limited tools and limited time before consumables run low. Some repairs will simply be beyond what you can do. Replacing an entire main pressure shell panel, rebuilding a large radiator field, swapping out a reactor core, or repairing a heavily damaged structural truss might require equipment you could never afford to launch. You'll be forced into patch jobs, partial fixes, or shutting down parts of the ship permanently. So over time, a deep space vehicle doesn't just stay like new if you treat it gently. It ages, materials embrittle, seals and lubricants reach end of life, Moving parts hit their cycle counts, and your ability to do major overhauls is limited to the small workshop you brought with you. And behind that slow mechanical decay is something even more fundamental. All of this hardware, all of the biology, every redundant circuit and carefully chosen material is fighting a law that never stops. The longer you stay out there, the more chances the universe gets to break something you can't afford to lose. How do you handle disasters when every single one happens inside the only room in the universe you're allowed to breathe in? Start with one of the worst: fire. On Earth, you know the rough rules. Flames go up, smoke rises, you crawl under it, vents carry fumes away. And in the absolute worst case, firefighters and sprinklers exist. In microgravity, those rules break. There is no up, so flames don't form tall columns, they form rounded blobs around the fuel source. Hot gases don't rise, they just hang there and slowly mix. Smoke doesn't conveniently stack at the ceiling, it spreads out following air currents from fans and circulation systems. A small electrical fire, a cable that overheats, a battery that fails can fill a closed module with toxic gases fast. Not just heat, but combustion products you don't want in your lungs at any concentration. Your fire response options are narrow. You cut power to the affected rack. You try to smother it with a specific fire extinguisher designed for electronics in microgravity, and you consider sealing off the compartment. Venting the atmosphere of that space to vacuum could stop the fire, but only if you have somewhere else for the crew to go, and only if you're willing to lose that module's air and possibly its systems. You can't call a fire department, you can't step outside to escape the smoke. The people who are fighting the fire are also the people who will die if it spreads. In training, you can rehearse the steps, you can drill the muscle memory, but the real event doesn't come with safety observers and a reset button. It's you, your crew, and whatever tools you actually strap down in that room. Now take away the fire and poke a hole in the wall instead. How much time do you really have when your entire atmosphere finds a shortcut to vacuum? In a major hull breach, especially one larger than a pinhole, cabin pressure can fall from around 101 kilopascals, 1 bar, to lethal levels in seconds or minutes. The exact timeline depends on the size and location of the hole and on how big your pressurized volume is, but the critical fact is this: the clock is short, and you feel it. Your ears pop, your lungs strain, alarms scream. Every action you take is measured against how many breaths you and your crew have left in air that's still dense enough to use. You've trained to do the right things: identify the affected section, close hatches, switch valves, grab the emergency patch kit and slap flexible plates and sealant over the breach. But training in a simulator with normal air around you and no real vacuum on the other side is one thing. Doing it when a sensor is telling you pressure is dropping, your head feels light, and you know there is no rescue ship on the way is different. You might stop the leak in time. You might only slow it and have to accept a partial loss of atmosphere, burning through stored tanks. Or you might fail and watch the environment drop past survivable levels while you're still holding the patch in place. In deep space, depressurization is not a rare corner case. It's one of the default ways hardware can kill you. And all of that is just the ship. Your body still carries regular failure modes too. How do you handle routine medical emergencies when the nearest hospital is a dot of radio noise on the other side of the solar system? Appendicitis, heart attacks, strokes, severe infections, broken bones from impacts or awkward motions in partial G, none of that stops just because you're off Earth. Biological failure doesn't look at mission plans. On the ship, your medical kit is limited by mass and volume. You might have some imaging, basic lab tools, and 1 or 2 crew with medical training, but you do not have a full surgical suite, intensive care beds, or teams of specialists. Procedures that are standard on Earth, like removing an appendix, dealing with a blood clot in the brain, or repairing a complex fracture, normally rely on staffed operating rooms, specialized tools, sterilization facilities, and blood banks. In space, you're working with what you brought. In microgravity, where blood doesn't pool, where instruments float if you let go, and where any serious infection is happening in a closed environment shared by the entire crew. Evacuation is off the table. There is no emergency capsule that can get you back to a hospital in hours. At best, you can stabilize, manage symptoms, and hope the problem doesn't require full-scale surgery. That changes the risk calculus of every little thing. A minor injury you'd shrug off on Earth can be mission-changing if it spirals in the wrong direction. Meanwhile, the ship's systems are wired so tightly together that one fault almost never stays alone. What happens when the emergency isn't local at all, but a cascade? In a highly integrated system, losing one function odds often hits several at once. Lose main power, and you might lose primary life support blowers, main communication arrays, and active thermal control in the same instant. A single coolant leak in a main loop might overheat critical electronics, shut down processing units, and cause those units to mismanage the very pumps and valves that could save you. Software that's supposed to handle faults can itself be running on hardware stressed by radiation or heat. A problem in one rack can ripple through shared power buses and data lines. Instead of a pump failed, replace it, you get this pump failed, which overheated that controller, which glitched the CO2 scrubber logic, which now thinks everything is fine while levels climb. You don't just walk up and swap one box. You're trying to stop a chain reaction in a live, fragile system where every action has side effects. The timelines are short. If cooling stops, electronics don't wait politely. They drift into temperature ranges where errors multiply. If oxygen recycling's mismanaged, CO2 levels creep up in the background while you're distracted by a noisy alarm somewhere else. You can train for single failures, you can simulate some cascades, but real-life combinations will always find new paths. And all of this is happening inside human brains that get tired, distracted, and overconfident. You can build procedures, you can drill them over and over until people can run them half asleep. But humans are not robots. Over time, they get training fatigue. Running the same emergency sim for the 100th time with no real fire, no real leak, can push people into autopilot. They start skipping small steps, or they memorize the exact training scenario instead of really understanding the underlying problems. In actual emergencies, stress cuts into performance in a different way. Too little stress and people underreact, assuming it's just another false alarm. Too much and they freeze, or they rush, or they tunnel in on one part of the problem and miss the bigger picture. The cruel irony is that the longer you go without a real major emergency, the more your brain quietly relaxes its sense of danger. The first real critical event after a long calm stretch can be the one where complacency and surprise team up to make everything worse. In deep space, the stakes are always at maximum, even when nothing seems to be happening. A missed step on a checklist can be the difference between a contained incident and a spiral of failures you can't pull out of. You can layer on automation and safeguards, but the final layer is still human judgment, human attention, and human reflexes under pressure. So after running through all these disasters, you hit the core reality behind every one of them. You're trying to maintain a small, complex, low-entropy bubble of air, water, food, hardware and biology in a universe that constantly pushes toward disorder, and you have no external backup. That isn't just hard, it's a direct fight with the most fundamental rule of physics about how systems evolve over the time. How do you win a fight against a rule of physics that says, very clearly, given enough time you lose? Entropy isn't a mood, it's a law. Any complex, low-entropy system, like a human body or a spacecraft full of precise machinery, naturally drifts toward disorder. Metal corrodes, lubricants break down, seals dry out, cells miscopy DNA, proteins misfold. On Earth, you push back using an entire planet's worth of resources. You eat food grown by global agriculture, doctors treat you in hospitals powered by huge grids, factories replace broken parts, specialists debug software. Energy and information are constantly being pumped in from a civilization of billions just to keep you at normal. In deep space, that funnel collapses. The energy you have is limited to what your ship can generate. The expertise you can draw on is limited to the few brains on board, plus messages from home that arrive late and in small chunks. Entropy is still working at full speed, but your ability to fight it shrinks to whatever you launched at the start. Every broken pump, every sick crew member, every corrupted file has to be fixed with the same small set of tools and knowledge, while new problems keep appearing. And the flow of information from Earth, the one thing that could help you outthink entropy, is itself throttled by distance. What does problem solving look like when call the engineers stops being a real-time option? On today's ships in low Earth orbit, something weird happens. You dump logs, photos and telemetry to the ground. Teams of engineers and scientists run simulations, cross-check data and send back patches, updated procedures or new workarounds, sometimes within hours. You're plugged into a giant external brain. Deep space inserts hard bottlenecks. Long light speed delays mean any message you send might take tens of minutes or hours to arrive. Bandwidth limits mean you can't just stream every sensor reading and camera feed like a live webcam. There will be times when you're out of contact altogether, behind a planet or blocked by geometry. Meanwhile, the rate at which new, unanticipated problems show up on board doesn't slow down. Where radiation hits, human mistakes, minor design oversights, those things keep happening at the pace they always do. The rate at which you can import solutions from civilization drops, but the rate at which you generate new failure modes stays roughly constant. Over a long mission, those curves cross in a bad way. At some point you will see a failure nobody rehearsed for, and you'll have to solve it with incomplete data and no chance to ask Earth in time. And that's just for missions measured in years. What happens when people start talking about interstellar trips, distances where even radio messages take years to cross? Even if you push a crewed ship to tens of kilometers per second, far faster than anything we've ever flown with humans, you're still crawling compared to the scale of the galaxy. At around 30 kilometers per second, roughly 67,000 miles per hour, reaching Proxima Centauri about 4.2 light years away, would take on the order of 40,000 years. That's longer than all of recorded human history. At that point, mission duration stops fitting inside a human lifetime. It stops fitting inside 10 lifetimes. Long-term survival in that regime is no longer a question of train a crew and send them. It's a civilization-level problem. You'd need generation after generation to be born, live and die inside moving habitats, with all the biological, social and technical issues we just walked through. A single human body or a single machine is not built to maintain identity over those timescales. Even social systems and cultures drift and fracture over centuries, let alone tens of thousands of years. And that's the heart of it. You, as a biological organism, are wildly out of equilibrium with deep space. The gap between what your body demands and what the universe offers is enormous, and that gap never closes. It has to be bridged non-stop. Your body wants to sit at about 37 degrees Celsius, around 98.6 degrees Fahrenheit, with liquid water inside cells, a narrow pH range, oxygen partial pressure in a tight band, and around 101 kilopascals of pressure on your skin. It wants a certain range of radiation doses, not too high, not too low, regular cycles of light and dark, and a constant flow of energy-rich molecules from food. Deep space sits at roughly 3 Kelvin, about minus 270 degrees Celsius in near-perfect vacuum with zero pressure, almost no free oxygen and radiation fields that are either too much cosmic rays, solar storms, or too little, no warm infrared background to casually keep your body in range. The natural rest state of matter out there is cold, diffuse and inert. Nothing about that matches what your cells need. So you build a bubble of controlled conditions and push energy through it, watt by watt, second by second, to hold back the drift towards the outside. Heat pumps run, scrubbers cycle, computers watch sensors and tweak valves. Any lapse, power drop, leak, component failure, lets the outside environment start dragging your little pocket closer to its own preferred state. There is no point where the system stays stable on its own. Stability itself is an active, energy-burning process. That's why calling human survival in deep, deep space impossible isn't an insult, it's a warning label. Humans can visit space, We can orbit Earth for months, maybe for a year or more with heavy support. We might build outposts on the Moon or Mars where gravity, atmosphere and local materials help a little. Those are extreme, but they're still tied tightly to planetary environments and Earth-based support. Deep space, real deep space, far from planets, far from steady sunlight, far from any resupply, is not a natural habitat. It's not like moving into a desert or building a station under the ocean. It's a medium you cross using machines and planning that all assume you're going back to a planet at some point. Treating it as a place you can casually live is like treating the inside of a running jet engine as just another room. If one day we do prove this wrong, if we build ships and societies that can truly survive out there for centuries or millennia, it won't look like a slightly better version of what we have now. It will require machines that almost never fail, self-repairing structures, life support that can run for decades without resupply, and human communities that can handle isolation, risk, and slow, relentless environmental pressure without collapsing. Compared to that, everything we've done so far, space stations, moon landings, Mars rovers, is just paddling at the shoreline of an ocean that doesn't care if we drown. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.